Hello and welcome to the first video of the FP3 chapter, Vectors. Start a question on the screen, pause the video now if you've got time to do this. Calculate the scalar product of these two vectors. Now remember, the scalar product is also known as the dot product and is defined as A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. There is a quick way of finding this out, and that is to multiply the elements and add them together. So 4 times minus 2 is minus 8, plus 5 times 0, plus minus 1 times 3 is equal to minus 11. So that's the dot product. Hence, find the angle between the two vectors. So if we can find the dot product in this method, that's the left-hand side, we know how to find the magnitude of vectors, and then we can find the angle by putting these together. So we've got minus 11 is equal to the square root of 4 squared plus 5 squared plus minus 1 squared times minus 2 squared plus 0 squared plus 3 squared square rooted times the cosine of the angle. Put all that into your calculator and you get the square root of 546. So the cosine of the angle, minus 11 over the square root of 546, and if you do the inverse cosine of that, you get the answer of 118 degrees to 3 significant figures. And notice that that is an obtuse angle. Okay, we've got 6 videos in this chapter. The 6th one is quite chunky because it does a lot of problem solving in different types of problems between points, lines and planes, but the other videos are not too bad. In this video we'll look at the vector product, we'll define it and use it. Then in the next one we'll interpret that as an area, the scalar triple product and its interpretation. Then we'll look at the different ways of writing equations of a line, specifically the vector equation and the vector equation of a plane, and then that chunky one on the end, putting it all together, solving lots of different types of problems. So in this video, the vector product of two vectors. And to explain this, I'm going to contrast it with the scalar product, which we already know. This is the dot product. It uses a dot and it's defined in this way. It's called the scalar product because it gives you a scalar answer, not a vector answer. A couple of things to note: this is good for finding the angle between two vectors, like we did, and it is also good for verifying that two vectors are perpendicular, because if the angle between them is 90, then this will all be 0, so the dot product of two vectors equals 0, tells you that those two vectors are perpendicular. It's also commutative. A dot B equals B dot A. Okay, in contrast to this, the vector product produces a vector answer. It's also known as the cross product because it uses a cross as its symbol. So both of these are similar to the idea of multiplying. So we use the dot symbol here and the cross symbol here. So A cross B is defined as the magnitude of A times the magnitude of B times the sine of the angle between them. And to make sure it's a vector, we put n hat on the definition here. So this is a unit vector in the appropriate direction. And we'll talk about the direction in just a second. This is good for finding a vector that is perpendicular to A and also perpendicular to B. This is a very useful thing, which we'll use a lot in the 6th video at the end when we're solving all the problems. To determine the direction, you can use this little right-hand rule shown here in the picture. You hold your hand out, your right hand, in this way, point your forefinger in the direction of the vector A, your middle finger in the direction of vector B, and you'll notice that these two fingers in this way will produce a plane, and your thumb will always be perpendicular to that plane. So your thumb shows you the direction of the answer vector. If you were to use your left hand, it would be in the opposite direction, which would be negative. You wouldn't have the right answer. So it's specifically a right hand rule. Nice little animation that was available on the internet here shows you the answer for various types. So you can see A is fixed, B is going around the circle, and the blue arrow that's changing is the vector product of A and B. It's very important to note that this is not commutative. That links with the idea of using your right hand, not your left. If you use your left hand, it'll give you the same axis, but not the same direction. So you'll get the negative. So it's useful to note this. It's not commutative, no, but you can change A cross B into B cross A so long as you remember to put the negative in there. We'll use that as well. So that's the definition. Applying this to the unit vectors is a very useful thing to do because it will help us in the next few slides. Now remember, your unit vectors have a magnitude of 1, I in the x direction and so on, and we can use the right hand rule to decide what each of these sorts of things will equal. Let me put the definition here again. We've got A cross B, magnitude of A, magnitude of B, sine of the angle in between them, unit vector. So very quickly I'll walk you through this. I and j are unit vectors, so their magnitudes are 1 and 1, so it's 1 times 1. The sine of the angle between them, I and j, are perpendicular, so that's 90. Sine of 90 is 1, so that's 1 times 1 times 1 times the unit vector in the correct direction. So all we're going to have here is another unit vector. And to figure out the direction, you can use your hand, point your forefinger along I, your middle finger along J, and your thumb should point up the Z-axis. So this will give the answer K. And then if you can twist your hand enough, and you point your forefinger along K, your middle finger along J, your thumb should point along the negative x-axis, which gives us the answer minus I here. And if you were to do I cross I and point your two fingers in the same direction, hopefully a quick twist of your wrist will convince you that your thumb could point in any direction on the YZ plane, and this is 0. A better explanation for that is, of course, if you've got two vectors parallel, the angle between them is 0, and the sine of 0 is, of course, 0. So all of this becomes 0. So to note that if two vectors are parallel, or if one of them is 0, then their cross product is 0. And the other 6, we've got these 3 here, and the other 3 to give us 6 down here. A quick note on these: if you want to be able to remember these, and you look at it in the reading direction left to right, I, J, K is positive. I, J, cyclic brings it back round to K. I, J, K. So all of these are positive, and if you can't do that, I, J, no. If you've got to go backwards, then it becomes a negative. I, J, no. I, J, K. I, J, no. I, J, K. So that's a quick way of remembering which ones are positive and which ones are negative. Okay, we're going to use that to help us figure out another way of finding the cross product. Because as with the dot product, we've got two ways. It's better if we can find the left-hand side of the equation without knowing the angle, so that we can use that to help us find the angle. To do that, we're going to use what we've just talked about. Because here, if we've got the vectors A and B, we can write them in their ijk form, and then we can multiply this out in the normal expanding brackets way. I'll do these 3 terms, and then we'll summarize the rest of them. So we've got A1 I cross B1 I. This is the first term that comes out of this. We can write that as a1, b1 because they are just scalars, I cross I. And I cross I we've just seen in the previous slide is 0. The second term, a1i times b2j. Now because this is not commutative, it's important to keep what's on the left of the cross on the left, and the term on the right of the cross needs to stay on the right. So we have a1, b2 again, these are just numbers, and then I on the left cross j on the right. And I cross j we saw was equal to k. The third one, this cross with this, gives us a1, b3, I cross k, which we saw on the previous screen is minus j. Okay, I won't do it with all of them, but you can see you're going to have another 3 terms here, and another 3 terms here, and if you do all of those and you collect them together, you get this. You can see this answer a1, b2k here, and this answer minus a1, b3j here. And of course the 0 doesn't come in. And then you can put this back into column vector format, and here is a reasonably quick way of finding the cross product of 2 vectors. This is given to you in the formula booklet, the definition, this way of finding the answer, and also this here, which is to do with matrices, which we'll talk about in chapter 6. For my part, rather than going back to this every time, I like to use a little fish symbol process. I'll very quickly show you what this is, and then you can understand what I'm doing when I do it on the video. If I want the top row answer, I don't use the top row elements, but I start with a fish symbol, top left, round to the bottom left. I'll do that again. So we've got a2 times b3, and when you start coming backwards, it's minus b2 times a3. And that gives you this answer here. Then if you want the bottom row, you can do the same thing. a1 times b2 minus b1 times a2. And that gives you this answer. And I've left the middle row to last because the middle row you have to go backwards, starting at the bottom left, not the top left. a3 b1 minus b3 a1. And that gives you this answer. If you understand that and you like it, take it away. If you don't, ignore it, that's fine. It's here in your formula booklet. So let's actually use this in an example. Given that a is 2 minus 3, 0, and b is 4, 1, minus 1, find a cross b. And you'll notice I tend to put my vectors into column format so that I can then use my little fish symbol process. So for the top row, I do minus 3 times minus 1, that's 3, minus 1 times 0. For the middle row is 0 times 4, 0, minus 2. And for the bottom row, 2 minus 12. Which gives me the answer 3 to 14. Part 2. Verify that A cross B is perpendicular to both A and B. Okay, like I said, the cross product should give us a vector answer that is perpendicular to both of these. And using the dot product, we can verify that this is true, because if you dot 2 vectors that are perpendicular, you should get the answer 0. So in order to do this, we take the answer 3 to 14, do the dot product with A, and this needs to give us 0. So 3 times 2 is 6, plus 2 times minus 3 is minus 6, plus 0 times 14 is 0, so yes, that is perpendicular to A. And then verify it with B as well. 4, 1, minus 1, dot 3 to 14. 4 times 3, 12, plus 1 times 2, 2, minus 1 times 14 is 0 as well. So yes, we have verified that this answer vector 3 to 14 is perpendicular to both A and B. Another example, very similar, but this time find a unit vector perpendicular to this and this. So to find the perpendicular vector, we do the cross product. So the top one, 9 minus 6. Middle one, 16 minus 12. And the bottom one is 12 minus 24. So that gives us 3, 4 minus 12. But this is clearly not a unit vector. If you find the magnitude of this, 3 squared plus 4 squared plus 12 squared, that will not equal 1. But we do need to know what that is to find the unit vector. And some Pythagorean triples here. 3 squared plus 4 squared would give me 5 squared, and 5 squared plus 12 squared would give me 13 squared. So the magnitude here is 13. So the unit vector, if I call this n hat, will equal 3 divided by 13, 4 divided by 13, minus 12 divided by 13. Like this. Okay, final example. Find the sine of the angle between the vectors this and this. Okay, the sine of the angle is using the cross product. Like this. But here we're going to do something so that we don't need to worry about it being a vector. Because we don't want a vector answer here, we just want to know the magnitude of the sine of the angle. So to do that, what we're going to do is find the magnitude of this cross product. Because if I then do the magnitude on this side, the magnitude of A times the magnitude of B times sine theta, that's already just a magnitude, it's already just a scalar. And the magnitude of n hat, because of the hat, this is a unit vector, that's just 1. So doing the magnitude of the left-hand side is effectively getting rid of the vector element on the right-hand side. So this is going to be useful in this question because I want to know sine theta, not the whole vector. So to do this, same as before, we're going to need to find A cross B. 2, 1, 2 cross 0, minus 3, 4. Top element is 4 minus 6. Middle element 0 minus 8. And the bottom element minus 6 minus 0. So we have 10 minus 8 minus 6. Now I want the magnitude of this. So the magnitude of 10 minus 8 minus 6 is equal to the square root of 10 squared plus minus 8 squared plus minus 6 squared, which gives me the square root of 200, which is 10 root 2. And then very similar to the dot product process when you're trying to find the angle, we need to find the right-hand side magnitudes. So the magnitude of A is equal to the square root of 2 squared plus 1 squared plus 2 squared, which is a nice easy number 3. Magnitude of B, 0 squared plus minus 3 squared plus 4 squared, also a nice number 5. So putting these three things together, we can write that the left-hand side, 10 root 2, the cross product, or the magnitude of the cross product of A and B, is equal to magnitude of A, 3, times the magnitude of B, 5, times the sine of the angle between them. So the sine of the angle is 10 over 15, so that's 2 over 3 root 2. And because we took the magnitude of the left-hand side, I don't need to worry about the vector here, because this is a unit vector. So the sine of the angle is 2 root 2 over 3. Now from there, it might seem like we could get the angle very easily, but be careful. I would suggest the dot product is a better way of finding the angle itself. Why is that? Because with sine, remember, there is some ambiguity as to whether you have an acute angle or an obtuse angle. Your calculator will never give you an obtuse angle from a sine function, an inverse sine function. If you need to know the angle, I would suggest, unless it's clear in the question that it is either acute or obtuse, I would suggest you use the dot product instead to remove that ambiguity. I would also suggest it's a good idea, if you've got a scientific calculator that can do vectors, that you find out how to use the vector mode, and you get used to calculating quite quickly the answer in vector mode so that you can check your answers when you're doing this. It's very useful. You can't do this in an exam, obviously. You need to show you all of your process to get the marks, but it is nice to be able to confirm that you have got the right answer. And you could do that by doing the questions from the textbook, exercise 5A, and then using your calculator to check that you've got the right answers for each of these. And maybe I'll see you in the next video.